Alright, time for another draftphysics.com, debatephysics.com also, but you can't get any of these people to debate. So I have tried to contact, like Veritasium. I did offer Veritasium $4,000. And I know I offered Steve at least two. I think I open-ended it. I think I said it could be more if you insist. Um, to do a kinetic energy video to deal with the fact that, or a double slit video, something connected, okay, to these basic duality problems that physics has. And this one relates, to the kinetic energy one, obviously, because the word energy is going to be used when talking about entropy, but also relates to Einstein's BS about absolute space being crap, and that somehow we live in some sort of shift-shaping universe where time is mutable, and it's a place time. It's not a it's not a function, and the idea that gravity isn't energy. So once they took gravity out of the energy cycle, they broke all of the physics, because, and that's why they can't see something so obvious, that obviously there's no entropy problem in the universe, because gravity's constantly doing exactly the opposite of the divergence. It's creating convergences, and it's making packets of energy all the time, consolidating energy into batteries, and then the batteries drain, and then they're consolidated, and then they drain, and it's a perfectly renewable cycle, and there is no heat death by entropy. Entropy is not a good reason to say there's going to be a heat death. Okay, anyway, it's just really bad physics. So this was cited by the Veritasium video as a reference, and frankly this video is better, but it's still bad. So it's still moldy science. All right. Sorry, that wasn't my fault. Okay, it wasn't. It just happens to be where I could get the pop-up window there. That's better. Okay. Anyway, so it seems likable and a nice guy and all that kind of crap, but these science presenters really don't know what the hell they're talking about. And there's a real contrast here too, in the sense that this video got 87,000 views, where the Veritasium video got 14 million. What sense does it make? But it's all bad. It's millions of bad descriptions of energy in the universe.
I thought I'd film this video on a train. It's a weird train though, it hasn't moved for about an hour. Also, outside the window, it's just another window. Also, this side, it's just curtain.
Whatever. So it's always a little joke, and that one is so bad. Oof.
There's no train on that side. It's just train on this side. Anyway, this video is about entropy, and you've probably heard of entropy. Maybe you think of entropy as a measure of disorder, and you know that entropy is always increasing, so that the disorder in the universe is always going up. This is like the popular...
So again, this is just an expansion and contractions, and that's all you're really talking about. Expansions are intrinsically spread out, and the contractions are doing exactly the opposite. Every single piece of energy you throw into the universe, you can imagine that I could throw a wrench in the universe, and and it's going to hit something. And when it hits something, it's this now compressing energy. There's now more energy in the same location. There's more matter in the same location. So I'm going to constantly consolidate. Everything I break apart is somewhere else going to be a compression, and vice versa. So it's the default appearance. Okay, I hate to call it the simplification. The obvious part is that there's nothing obviously showing that the only place energy goes is to smaller and smaller things, when clearly very small things are making very compact things through gravity. Every time a photon hits the Earth, it's hitting the Earth with energy. The energy goes into the Earth. It's collecting it. I mean, except for the stuff reflected, of course.
One-line definition of entropy, that it's a measure of disorder. I'm not a big fan of it. I think it's kind of confusing and it doesn't help with your understanding of what entropy really is. I know it's a popular definition.
So it's a word they should have never invented because it's not really a concept. They should just called it what it is, that energy can be diverging or energy can be converging. It can do both things. And in this universe, it seems to do converging more than it's doing diverging. There's more gravity converging things than any supernova diverging things.
Because it's like, you know, the reason my room is always messy is because I'm constantly battling the universe's desire to increase in disorder. But there is a better definition.
So yes, that's really bad, but he's just going to defend that exact statement. He's going to defend the statement that somehow there is more disorder and that somehow this universe doesn't give a shit about order or disorder, and it's been running a long time, and it's not running in one direction.
Than that. This definition goes back to why entropy was invented in the first place, and it's to do with
because it was the 1800s and science was really dumb and Newton was dead. So once Newton died, reason died and nobody was reasonable anymore. So they believed in 1/2 mv squared, and they started really believing in wavy stuff. Woo, elemental woo, wavy little wavy waves. Okay. And yes, that's the definition of kook. So they all became frickin' kooks.
how engines work and making engines more efficient. So you know how an engine works. You put fuel in, you burn the fuel, that creates heat, and then somehow this heat is turned into the movement of your engine.
So it can just be viewed as a stream. Energy is always moving. It's something moving. So you can have chaos moving, lots of fish going in different directions. You could put a border next to them and some of the fish will hit you, and you can collect some of the energy of some of the fish. But if you can get all the fish to go the same direction, that is, put them in a pool and then only have one outlet for the fish, that is, only one way for them to get out of their noisy place and go to a quiet place, you can take advantage of that, because the fish will say, I don't like being crowded, and they will go to where it's less crowded. And energy is doing the same thing. So the fact is, you can take advantage of streams. So you can stick a water wheel in a river and collect some of the energy. And the same thing with gravity. You can collect the stream of gravity. You can poke into it and collect energy out of it. And that's all you're doing, is saying, and it doesn't matter whether the stream is going in, like the case of gravity, creating, charging a battery. You can steal some of the energy when the battery is being charged, or you can steal energy when it's being discharged. An explosion.
And that description is okay, but it's a lot more interesting than that. To illustrate the point, I've brought an engine with me. This is a very special type of engine that you don't put fuel in. Yeah, that's right. Free energy.
Okay, so obviously he is putting fuel in. Okay, everything that's warm is fueled by fuel. So there's some sort of engine that created the heat that's in a concentrated location. So you're going to take energy, heat, and use that. All right, so this isn't a this isn't a Carnot engine. This is, but it's similar principled.
People, it's real. The big energy companies are liars. No, that's not. Sorry. This is an example of
The big physicists are liars. I mean, they can't describe mv squared accurately. In the real world, they can't get that right, and they can't get the double slit right. And then they create silly entanglements and Copenhagen interpretations and all kinds of nonsense. Even Heisenberg, a completely unproven statement about some idea that somehow you cannot possibly ever, measure accurately particles, where you can't physically measure them. Well, it's a truth. You can't make a ruler small enough to measure something really small.
External combustion engine as opposed to an internal combustion engine. It's a Stirling engine, and you don't put fuel in, instead you burn your fuel on the outside. And
so you just take advantage of the fact that energy is going to move from hot to cold, and that's it. And so this has basically a spring in it. The flywheel isn't really going to do the work. The foam is going to do the work of creating the second cycle. And but there's nothing, we've been over it, sort of thing, if you've watched the previous videos. So it's not all that.
This is such a finely engineered Stirling engine that it will run just off the heat of my hand. Okay, so that bottom plate now has had a bit of a chance to warm up. It's now about the same temperature as my hand, so I just need to give this flywheel a little kick, start. It should just keep going.
So the static friction is still a problem. So you still have to overcome static friction, so it takes a higher level of energy to get it started than the energy to keep it moving. And that's because of charge. That's because whatever condition the cylinder is to the surfaces, all these things are stuck to each other by a little bit of static electricity. And that static electricity has to be overcome before you can get it to be capable of moving. What else do I need to say about that? Nothing.
Going on its own. It's the little engine that could.
So this really is, I don't know exactly the purpose of the foam, but obviously what's happening when it reaches the top of the cycle, something's happening that's cooling it. So either it's allowing air to get in, or it's doing something to make it possible to cool the air that's been heated. And it's got to be more than just, because once you go back into the compression cycle, it's just going to heat up again, and you'd end up back where you started, and you wouldn't be able to get a second cycle out of it. So the only way you get a second cycle is that air has to be cooled.
Actually, if I get it to the same level as my face, then they'll both be in focus. Huh.
So the foam probably has something to do with being a gasket, and it's controlling how much air is escaping.
To really get this thing going, you want to use something like a hot drink or a hand warmer.
So we have to do this part.
Okay. Looks like a little hot water bottle. Silly. Doesn't make any sense. It's not even a...
Yeah, it's really going. Some hand warmer. Frankly, okay, fine.
So let me explain how a Stirling engine works. There are two plates here. The bottom one is hot because I'm heating it with a hand warmer. The top one is just at room temperature. And inside...
So these are the plates of the bottom ones he's talking about, the two metal plates.
There's a block of foam. So if I move the block of foam to the top, then the air inside the chamber is in contact with the hot plate in... But obviously there has to be some way to capture the air without compressing it on the down cycle, because if you compress it, you're not going to go anywhere, because that's going to be work, and your engine can't do work. The bottom, so the air is warming up. When you heat up the air inside, it expands, and that expanding air pushes this piston here, so that pushes upwards, which turns the wheel. When you turn the wheel, that's connected to the foam block, so the foam block is now at the bottom, and when the foam block is at the bottom, then the air is in contact with the...
Okay, so it's two pieces of air. There's air in this little cylinder here, and then the piston, and then there's air below this thing, and all you're doing is using the piston air. This is the air that's changing temperatures, the one moving the piston. So there's basically two pistons in this device, so that complicates it.
The top plate, meaning the air cools down, meaning it contracts, meaning it pulls that piston back down.
So the piston pulls down because it took the hot air, went up into the piston, all right, and push the piston up. And then the piston is connected to all this metal that's cold. And so the cylinder of the piston, that air got cold because it's surrounded by this, it's connected to this top plate that's cooling it. So the hot air down here went into the piston, and then the piston was cooled by this condenser here, and that's why it pulled down. So the piston is the one that, this is the air. Is it airtight? Well, that's a good question. So the piston's connected to the bottom of this piston, the first piston, and that's what's going to move that piston. Is that right? No, there's no reason to have two pistons. Yeah, okay. Yeah, okay. So the heat from this goes into the bottom of this piston, right? So the heat from this layer goes into the bottom of this piston. So this is the airtight one. This is the one who cares. All right, and so this piston moves because it transferred the heat from this bottom plate into the bottom of this little piston. The little piston then heated up that air, and then the cold of the rest of this top metal cooled it really quickly enough to cause a contraction. That's it.
That turns the wheel some more. That,
I mean, these details aren't critically important to understanding, like how efficient this little engine isn't the important part. The important part is you're just taking advantage of heat moving from one place to another place. You're taking advantage of a stream of energy. That's it. That's all you need to know. Stream. And then just imagine the universe as energy streaming into all the gravitational bodies. And then you get the point that there's lots of examples of energy consolidating, okay, in the universe, and there is no tendency to become more spread out.
pulls the foam back up to the top, so now the air is in contact with the bottom plate, so it's expanding because it's getting hot, which is pushing the piston, which is turning the wheel, which is pushing the foam down, and so on and so on and so on. So that is how a Stirling engine works.
So you can really see the piston's moving exactly the opposite of this piston. So when this one's going up, this one's going down. Yeah.
But the point is, it's not heat that you need, it's a difference in temperature.
So you really should have put a diagram of this. You should have diagrammed this better. Because it's not as simple as it first looks. There's a little piston in here, and that little piston is moving exactly the opposite of this piston. So this air heats up when you've allowed more of it to exist here, and that's what heats this piston eventually.
So in this case, there needs to be a difference in temperature between these two plates. In fact, you can run this Stirling engine on ice. So if you have the bottom plate colder than the top plate, you can make it work, though there is no ice available on this train. So I'm just going to reiterate that. It's not heat that you need to run an engine, it's a difference.
No, so it's just about energy moving in a direction, and obviously it's easier to collect energy from a laser beam than it is a light bulb. So I can have 5 watts of energy. Well, yeah, to collect the light bulb's energy, I'm really going to be out of luck. Laser beam's going to be really easy. I can make a device to collect it. So some streams are easy to tap, some streams aren't. Some streams are so dense with energy that, it's really easy to put your water wheel in it because it's an endless supply, almost the Mississippi River or something. You can just make it bigger and bigger. You catch more and more water. Make your sail bigger and bigger, and then some streams are very small and you can only take so much energy out of them.
In temperature, like if both of these plates were really, really hot but the same temperature, it wouldn't run. So what's this got to do with entropy? Well, imagine you had 2 slabs of metal and one was hot, one was cold. You touch them together, what do you expect to happen? You expect heat to flow from the hot slab to the cold slab.
So, and it's just heat is momentum. Heat is energy. So it's just little pieces of energy. The pieces are hitting each other. The ones that have energy are giving the ones that don't have it motion. They're giving away their money, so to speak. So if you just thought of it as red being rich and blue being poor, you're just going to watch the money move from rich to poor.
Slab.
It can't go from poor to rich.
Until the heat is evenly distributed between the two slabs. And once the heat energy is evenly distributed, that's the end. Nothing else happens. You never see it in reverse. If you have two slabs that are...
Right, unless you put another cold thing next to it, and then you could pull more of that energy in just one direction. So you can always put something colder and keep creating flows of the energy, okay, from less and less hot objects. But again, it's yes, it is energy, but you can only collect it with the right collector. So a magnifying glass collects sunlight, and you could focus it onto a little beam, and you're doing something completely counter to any notion of entropy. You're consolidating it again.
Are at the same temperature with evenly distributed heat, you don't spontaneously see one of the slabs stealing heat energy from the other until there's a difference in temperature. So what if I put my Stirling engine between these two slabs? Well, heat would transfer between the slabs through the Stirling engine, causing the engine to turn. But once the energy has distributed evenly between the two slabs, then the engine will stop turning because the two plates of the engine are now at the same temperature. And this is the really important bit. Energy is only useful when it's clumped together. And when you use that...
So it's not really true, right? So, I mean, obviously, a nuclear bomb is... well, I suppose that's an example of the clump together, in the sense that now it's going to spread out. But what portion of the energy could you possibly use? So if you had a sailboat and a nuclear bomb goes off, well, 99.9999999% of the energy is lost. So you have to do something like a rocket engine. So a rocket engine's taking energy that will go in all directions. And with nozzles and openings and such, you're basically saying the only energy I'm going to extract is going to be moving in one direction. And so by using technology, you can take energy that's spread and essentially focus it like a magnifying glass and make it incredibly useful. Even though it's diverging, you're killing the divergence and forcing it all to go one way. Yeah, it's probably a perfect example of how, well, you really can capture the divergent heat. You just have to create the right device to allow it to only go out one way.
That energy, you're spreading it out, and once it's spread out, you can't use it anymore. It was during the...
So again, if you just make a balloon, it's a bunch of spread out energy, and then you can just open the valve on the balloon and make it go in just one direction. So again, it's perfectly is usable. You just have to create the right piece of technology to use it.
Industrial revolution that people became really interested in engines and how to make them more efficient. And it was here that the concept of entropy was born. It helped these early engineers to make their engines better. So my preferred one-line.
So that was just the idea of you just figure out this. It's not really about heat cycle. It's not about heat as much as it is about pressure. And the fact is heat just becomes your enemy. So what most engines became were engines that just got rid of a bunch of heat, okay, that just got in the way. Because it was too hard to convert it into motion. It was too hard to correct its divergence.
The definition of entropy is that it's a measure of how spread out your energy is. And we've already heard that entropy always increases, so that means that energy is always spreading out.
So it isn't. So again, I suppose if you took away gravity, then this argument might have some... I don't know, I'd have to think about the fact that, well, it's spreading out, but in a very cluttered universe, it can't spread out. It can't get anywhere. So it's almost like making the argument that you could create a photon in the center of the sun, and it's speculated that it takes it 1 million years to get to the surface. So, you can have a system that has the energy so dense that there's no way for the energy to actually spread anywhere. It's confined and stuck.
going from a clumped up state to a spread out state. And just as a side note, you can clump energy together locally, but it's always at the expense of energy spreading out somewhere else.
So, obviously the energy had to be somewhere else, and it could have been, a supernova, and then it creates energy that compresses, something else and just puts it from one battery into another battery. Or it can spread it out and go billions of light years and then hit another surface and turn it back into a battery. So it's just about how long it takes for a piece of energy to go from being storage to being free. Just as the energy is moving my hand here, I'm using speed of light forces to move my electrons and protons. They're not moving the speed of light anymore. But I'm using speed of light energy, all right, in its smallest form, the form that's pushing the matter, the form that went from force to material momentum. So you went from the momentum of a force, a photon, into matter moving much slower. But the momentum's still there, the force is still there, you didn't lose anything.
For example, this is actually a reversible heat engine. So if I manually turn this wheel, I can cause one plate to get hot while the other gets cold. So I'm clumping the energy together on one side. But to run this wheel, I'm using my muscles, and my muscles are putting heat out into the universe, and entropy is increasing that way.
Right, but you could be using it to take, for example, you could use some other consolidating mechanism like a stream, which is water that's now pushing down on the earth, and you could steal some of its weight, to turn your wheel, its momentum, and so it wouldn't be that you had to create any spreading of energy.
So the overall effect is that entropy is increased, even though I'm creating a local decrease in entropy. So energy is always becoming more spread out and less clumped together.
So it's just not a true statement. So that's just the point. This is just not a true statement. It's clearly not what's happening in the universe. It's clearly clumping all over the place. Our own bodies clump it. All kinds of things clump it. The oil in the ground is clumped solar energy. It's just wrong to say it's always, or that the net product of the universe is somehow the net product is less clumpy, when obviously you just look at the stars and yes, they're burning, but they're also being created.
What that means is, in the future, eventually, all the energy will be evenly spread out, and none of our engines will run, including our...
All right, so even if this were true, that somehow all of the matter was moving away from each other and everything started getting colder, the fact is gravity makes the things hot. So the fact is the gravity of every one of these big balls of something has a molten center. So there's always some place. You could always find your Goldilocks zone where you're protected from the cold universe with some layer of ice. And underneath that layer, you can find some place that's 72 degrees. So you could dig a hole in the ground and you'll find a place that's 72 degrees. There's a place. I mean, it's a little more complicated because of the geology and where the water moves and all of that kind of stuff. But there's going to be a place where it's going to be 72 degrees.
Bodies, which are a kind of engine, they'll stop running, but it's not all bad.
So all of that ain't going to happen. It wouldn't happen because gravity would still exist, because it's what they call bent space. Now, if the gravity is actually made out of energy diverging, then obviously it's still going to get colder, but you'd have to really spread it out to say you made it cold enough that there's no place that's 70 degrees anymore.
News for us humans. Fortunately, on Earth, there are loads of sources of clumped together energy that we haven't used yet. Clumped together energy that hasn't spread out, things like coal, oil and gas. When we burn those fuels, we're running our engines and we're spreading the energy out. So once we've burnt them, that's it.
So there's two parts to that story, right? There's a part of what you released as a gas, methane and other things you allow to get back in the atmosphere, the carbon. And the other side of it is that you just create a layer of heat on the surface of the Earth. So you are heating the surface of the Earth by expending the fuel and creating fire, essentially. You're just creating forest fires all the time. And so you're heating the surface layer directly and indirectly by creating greenhouse gases that are increasing the amount of energy the universe stores.
Can't use them anymore. The energy is spread out. So they will run out. They're non-renewable sources of energy. Fortunately, there is still one giant source of clumped together energy that we can use, and that's the sun. So once the fossil fuels...
So it isn't all that giant. I mean, 1,000 watts per square meter on the surface of the Earth. It's not that, it's not all that.
Run out, we can power our engines using things like solar panels. We can grow crops and make biofuels and things like that.
So, I mean, quite obviously, you're not going to run like a wheat combine by putting a bunch of solar panels on it. It's not going to go very far or very fast. So you're going to have to store energy somewhere else, from a gigantic farm of panels, to make much run.
By the way, I'm not endorsing using up all the fossil fuels on Earth, because there are some terrible side effects from doing that. For example, pumping CO2 into the atmosphere. So we should really be switching to that massive clump of energy, the sun, sooner rather than later. Of course, all the energy in the sun will eventually spread out as well, as will all the energy in the universe. And once...
So they keep saying it, right? And the universe has every sign of reclumping. So every piece of radiation that hits the Earth from Alpha Centauri or any place, it's all putting pressure on the Earth. It's all compacting the Earth. So it's just wrong from even their perspective. Now, obviously, I think gravity is a photonic force. That is, it's photons that don't have a pattern. And so there's a whole pile of energy in the universe that we can't see because it doesn't have a frequency. And that's doing gravity's job.
So all the energy in the universe is evenly spread out.
The universe is really hot. The empty space is hot with energy. It's just no matter for it to heat. And we can only see the energy when it heats a piece of matter. So it's invisible, until it heats a piece of matter, till it gives matter momentum. We can't detect it. Can't detect the energy in the universe, the stuff moving the speed of light, until you make it give its momentum to a piece of matter, an electron or a proton.
Nothing interesting can ever happen again.
So I'm just saying, even if this were true and it was all going to happen at this hugely accelerated rate, if we had to, all we'd have to do is go under the crust of the Earth, and we'd be fine. Because that's an energy source. It's hot down there.
Do we need to worry about this? Well, this is called the heat death of the universe, and it's science's best guess at how...
So again, it's not a very good guess. It's a really shitty guess, especially in the context of over the last... I think I was a kid when I saw National Geographic shows where they showed the heat vents in the bottom of the ocean and speculated that that cycle, where heat is turned into life, without any sunlight at all. So you have zero influence from the sun, and all of the biology is completely dependent on chemical energy created by the heat. And that works.
How the universe will end, but it won't happen for another 10,000 trillion years.
So that I take a bunch of those trillions off if I don't try to go to absolute zero. So if I don't go absolute zero, if I just go like 32 degrees, it's not trillions of years by their diagram. So it just depends on how cold you're talking about.
So why does entropy always increase? Well, it's actually a statistical phenomenon.
So it's really not. It's a statistical phenomenon that energy moves from places that have it to places that don't, that's a fact. And that's all there is. And it can do it in different ways. It can do it with a laser beam, or it can do it with a bunch of spread out light. And there's no rules about that. But the fact that it has to find, it can't, something can't move into more pressure. You can't shove the money in if the box is full.
You had a cardboard box and you have a layer of ping pong balls at the bottom. Half of them are red, half of them are blue.
So it's exactly the same formula. So each one of these videos has the same formula of talking about these two different subjects. You know, the probability of, you know, patterns and having enough permutations to create different patterns. So if I only have 3 dots, I can't draw Bugs Bunny. But I can draw Bugs Bunny if I have 100,000 dots. That kind of thing.
And you've painstakingly arranged them so all the red ping pong balls are on one side, all the blue ping pong balls are on the other side. Now, vigorously shake that box. All those ping pong balls are going to fly around, then let them settle again into a single layer. And you'll notice that the red ping pong balls and blue ping pong balls are randomly distributed throughout the layer.
So that's not what you're going to notice, because there's almost a, you know, there's a 50-50 chance it won't be 50-50. You know, so the fact is, it's always going to be a little bit, you know, there'll be 10 on one side and 9 on the other side, or some kind of thing like that. And so what he's saying only works when you have 1,000,000 ping pong balls. Then you can be assured what your outcomes are going to be looking like. But they're never still going to be perfectly random. There's still only one perfectly random in some sense. In some sense of a perfect random pattern of on, off, you know, red, blue, red, blue, red, blue.
You won't find that you have, you know, all the red ping pong balls on one side and all the blue ping pong balls on the other side. And you probably just have an intuitive understanding of why that seems obvious. But just to give it some statistical rigor, there is only one way to have all the ping pong balls that are red on one side and all the ping pong balls that are blue on the other side. But there are so many other possible arrangements, millions, billions, trillions of possible.
Right, and it's only trillions if you start with billions or millions, you know, so that's sort of an exaggeration. If you start with 10, well, then you got a 1 in 10 chance.
Possible.
Something like that. Might be 1 in 100, but anyway, it's a much more likely.
Gazillions of possible arrangements, depending on how many ping pong balls you've got, of having them in that layer. So there's only one out of trillions that is that kind of clumped together state. So clumped together is statistically unlikely. And when you scale...
So again, and that's obviously not true in the universe, because there's a mechanism, that is, the system itself captures diversity. It captures divergence, inevitably. And it reconverges it through gravity. It repressurizes something. The pressure always goes somewhere, and it always goes back to repressurizing something.
That up to, you know, a box of atoms where you've got hot ones on one side and cold ones on the other, and they're all whizzing round. Just by chance, they could all whiz over to one half of the box, leaving the cold ones on the other side. But it's so unlikely that we never ever see it happen.
I guess I wouldn't argue that you never ever see it happen. So I mean, you do a computer simulation or something, and you know, you could run it for 10 years and whoop, there it is. So it's not like it's never going to happen.
What's interesting is that you can look at time itself, the passage of time.
So this is the other part. So they all throw time in here, and somehow time has something to do with this simple cycle of expansion, explosion, and then contraction. And that somehow this is time. Well, any motion is time. Any motion is less than instantaneous in this universe, and therefore time exists. You can't have time if everything's moving instantaneous speed. Then everything already happened instantaneously, and you're all done. but it doesn't. And so that's why there's time. But time just has to do with the fact that there is no motion that's fast enough, not to create time.
The direction of time, the arrow of time, in terms of entropy, you can define a direction.
So this is just, even having a conversation about some idea that time has an arrow, well, where do you get that from? I mean, it's just clear the past is gone. It's done. It already did its thing. It's no longer exists. All the pieces are in some new place. You can't go back to the old place. There was no place. Time is not a location. I mean, how, it's just so stupid. And the future is likewise non-existent yet. Okay? I mean, it's going to be inevitable what happens, because everything's going to obey very strict physical rules about its eventual trajectory. And all of that we can understand. The water is going to fall off the waterfall. It's going to obey the rules. I can predict where the water will be in the future. But the future isn't here. It's not a place. You can't go there. It takes time to travel distance. Anything that's moving is moving distances. And we can't travel those distances without traveling the distance. We can't get to that until we travel the distance. We have to use time to get to a timed place, a place in time.
For time, in terms of the spreading out of energy, in terms of the increase in entropy. So there's an argument that time itself...
There's an argument. Whose argument? Why are you proselytizing it? Why would anybody even connect these two subjects at all? Time only exists because motion is slow. Some degree of slowness. Everything in the universe is moving some degree of slowness. Therefore, there has to be time.
It's a statistical phenomenon.
Terrible bullshit. Okay, and then I guess he might have got his little engine for free, and so he wants to do a commercial for it. I'm not saying that. No, I won't say that. See, there it's running faster, but you can see the little piston. So this is the real catch. The piston's moving in the opposite direction of the heat capturer. Okay, the opposite cycle.
This stunning engine.
Got to figure out what this other thing on the other side is doing. So there's a piston on one side, and then there's another thing on the other side. Yeah, see, this is more complicated than he described it. But anyway, the principle is just that simple, though. You're just taking advantage of, it has some direction, the energy, in the sense that it's, there are hot and cold surfaces, and it can only go in one direction from hot to cold, and you're taking advantage of that. But this isn't highly efficient. Okay. In any way, the more work you make it do, the more energy you have to put in. More heat. More of a differential, I guess is the way to say it. Alright, so, and it just proves that you can capture energy from something that's hot. You just have to find something cold. And, that's all basically it takes. Alright. Probably enough. Definitely enough. But anyway, it's worth pointing out. So all of this is just, it's really sloppy. And again, it's taking the engineering of this engine and extrapolating it to some idea that the whole universe is nothing but energy going from clumps into spread out, when it's just so obvious that's not what's happening in the universe. It's clumping all over the place.